So first I would like to thank the organizers, I don't know where, so for giving me the opportunity to present our work at the Langevin Institute. I hope you're not too tired by the barbecue or dinner. And yes, and I would like to thank you to be here for listening this talk. So today I'm going to talk about a matrix approach of wave imaging that has been already introduced by Matthias yesterday morning. But this time I will show how we can go from the human body to passive seismology. And of course, this work is a collaborative work with Matthias and Michel. And here are Elsa Giroda and Rita Touma that are in this workshop. And they are the poster. So if you have you can go after the talk, go and see the poster, and they can answer to all your questions. Okay, so at the Langevin Institute, we are interested about wave propagation in complex media, multiple scattering, etc. But from a pluridisciplinary perspective. So we are interested in imaging applications, whether it be with light, ultrasound, or seismic wave. And for all these applications, imaging methods suffer from the same limitations that are due to the medium inhomogeneities, and these limitations will be aberrations and multiple scattering, so I will define them later. And our holy grail is to build a universal and non-invasive approach of wave imaging in complex media. So today, I will not talk about optics. I will introduce the reflection matrix approach with an ultrasound proof of concept applied to some clinical case. And then I will move towards the seismic imaging by showing two examples in a complex area, a fault zone, the San Jacinto fault zone in California, and the La Soufrière volcano in Guadeloupe. And at the end, I will show you how we can take advantage of the matrix approach, not only to build an image of the reflectivity of the medium, but also to map parameters such as the wave velocity or also transport parameters in 3D, only from reflection measurements. Okay, so let's start with ultrasound imaging. So I start from the basis. So how to build an image. So imagine that you have this dolphin in the Bay of Cargès, or Matthias, without he had his time reversal mirror. He was just shooting to detect the meru that was hidden in the rocks. And what you can do is to send an ultrasonic wave, for example, like a dolphin, and then this wave propagates through the sea, and at the end, it can be reflected by fish that are inhomogeneities in terms of density and compressibility, and echoes are coming back towards the emitter. And based on the information on the time of flight that the echo make to come back, you can locate you can image these scatterers in the axial direction. So this is exactly the same principle that followed Paul Langevin in 1915 to build the first sonar. So now your fish is replaced by a piezoelectric transducer. You apply an electric pulse to this piezoelectric transducer. It converts into a mechanical wave, and then you get the backscattered echoes that you can analyze then on your oscilloscope. And you have these two signals that are associated to two scatterers that are at different depth. And like that, you can discriminate between scatterers that are located at different positions. But the problem is that you're limited by the only axial resolution. Here you only have an axial resolution, and you're not able to discriminate between these two scatterers that are at the same depth. So to have an information on the lateral axis, you need a focusing process. So this can be done with a concave piezoelectric transducer, and in that case, you will focus on one specific position. We'll retrieve the signal along this line of the medium, and then you can scan the piezoelectric transducer to retrieve the lateral information. Okay, so very basic echolocation principle. So now, what happens when later people in the acoustic community started to use this wonderful probe ultrasonic probe that is made of an array of piezoelectric transducers. And then you will not have to scan your probe, but you can use electronic delays applied to each piezoelectric transducer in order to focus whatever you like in the medium. So to build an image, typically, you apply this parabolic phase delay, and it generates a cylindrical wave that will focus at a given depth inside the medium. And based on this incident wave, then the scatterers inside the medium scatter the incident wave field, and then you collect the backscattered wave field on the transducers. Okay, but you illuminate all the depth of the sample. So then you need to use the temporal information to be able to build an image. So to do that, you will make a fundamental hypothesis, which are a homogeneous medium with a constant speed of sound. The fact that the scatterers are only the incident wave is only scattered once by each scatterer of the medium. And in that case, you still have, if you check these two conditions, you still have a direct relationship between the scatter depth and the echo time of flight. And then you can, in reception, you can apply time delays such that you may interfere all the scattering events coming from this point, the echo coming from this point, by applying this time delay. And then you can realign all this data, sum them together, and then you will have a strong signal if you have a specific scatterer at the targeted position. And this signal, at the maximum, gives you 1 pixel of the image. Okay? And then you can look at the signal at a larger time of flight. It gives you a second pixel. You do that for all the depth, for all pixels contained in the depth of field of the incident wave. Okay? And you scan the phase laws, so just moving these time delays in this direction, and you can rebuild all the image, a part of the image like that in the depth of field of your incident wave field. And then if you want to recover the ultrasonic image in other location of the medium, you re-emit a set of incident wave to retrieve the whole image here of a lever. Okay. So each image is built from a single insonification, and so you need many insonifications to get a full image of the lever. So typically, as Matthias said yesterday, the frame rate is around 50 images per second. So this image is interesting. It's an estimator of the medium reflectivity, so it's only qualitative, okay? But it's related to the fluctuations of the impedance inside the medium, as said by Ludovic yesterday. So in this image, we have typically a different kind of scattering events. You can have specular reflectors, which are the organ walls. You can have low reflectivity areas, such as veins, vessels. And most of the time, you have this ultrasonic speckle, which results from the random distribution of unresolved scatterers. And you have a random interference between all the scatterers contained in the same focal spot. Okay? And this will be very important for ultrasonic application because we can use this ultrasonic speckle to improve the focusing quality inside the medium. So, yes, so one problem in ultrasound imaging is that the fundamental hypotheses I told you about before are not checked, actually. Because the medium has to go through several layers that display a different wave velocity, so typically fat layer, muscle layer, lever, they all display different wave velocity, and this difference of wave velocity it can be quite large when you inspect, for example, lever. So this long scale variation of the speed of sound will result in what I call aberrations, or phase distortions of the wavefront, and they can alter strongly the image resolution and contrast, especially when you want to make a diagnosis, you want the image to be the best, to take the best decision. On top of that, you can have multiple reflections between organ walls, okay, here between the skin and the liver, the surface of the liver, and it can lead to reverberation artifacts, and that again can prevent from seeing some interesting feature in the image. And on top of that, something that is generally completely neglected in ultrasound imaging, you can have multiple scattering. meaning that the wave is scattered several times before coming back towards the probe. And this contribution was completely, actually, not considered in ultrasound imaging, and I will show you that it is far from being negligible in this kind of image. And most of the time we say, okay, it's ultrasonic speckle, it's just a reflection from the medium, random reflection from the medium, and most of the time it can be a large contribution of this speckle can be due to multiple scattering. So it has a strong impact on the analysis that we can have on the image. So the idea is to quantify this detrimental effect, to compensate for them, and to use them eventually to develop novel imaging modes, map the wave velocity, map scattering mean free path inside the medium. Okay, so to do that, Matthias already showed yesterday that we have a very nice tool, which is a reflection matrix. So the reflection matrix can be measured in different bases. It can be the canonical basis, meaning that one transducer is emitting an incident wave, a cylindrical wave, and then you collect all the backscattered wavefront on your probe, and then you can switch the source, and you can get all the impulse response between any transducer at the input and any transducer at the output. So this is the canonical reflection matrix. It's very nice because you have all the information on the medium, okay? You have access to all the degrees, spatial degrees of freedom that the probe can allow you. But it can be not so practical because you have only one transducer that is firing a pulse, so you have a problem of electronic noise. So then you can use what Matthias showed yesterday, plane wave insonification. And this plane wave insonification is very helpful in terms of signal to noise ratio and also in terms of frame rate, because you can, instead of firing the number, for example, 128 times the number of transducers that you have on the probe, you can use a few plane waves to illuminate the medium, and you can get an image with a good quality at a much higher frame rate. But you lose a bit of information on the medium, so it can be quite important if you want to compensate for aberrations and study multiple scattering. Anyway, so this is like that we collect our reflection matrix, sending different plane waves with different, by applying these linear time delays. And at the end, we get the impulse response between any plane wave at emission and transducer at reception as a function of time. So this will be our tool, and the reflection matrix can be measured in any basis you want, and then I will show you that with simple mathematical operations, you can jump from one basis to another, the plane wave basis to the transducer basis to the focus basis. Okay, so you can, the reflection matrix provides a response of the medium to any insonification, and one particular important basis here will be the focus basis, meaning that you can simulate, once you have your reflection matrix, you can simulate focusing inside the medium at any point, okay? And then you can look at the response that you're gonna have between any virtual source inside the medium and any virtual transducer inside the medium acting as a microphone, okay? So you can have multiple loudspeakers and multiple microphones, and by studying the response between any point inside the medium, you will deduce some important information on it, and local information. So typically, so we will project this reflection matrix in the focus basis, both in transmit and receive modes, and I will have access to the spatio-temporal focus reflection matrix with R in and R out, mapping the whole medium. So, check, yes. So then, how can we jump from one basis to another? So we can do it by applying time delays, and usually people in ultrasound imaging are doing that. Here I will consider, rather, I will go into the Fourier domain because it's easier to handle. You can jump from one basis to another by a simple matrix operation. So first Fourier transform, then apply some transfer matrix on each side of the reflection matrix. So it can be the transfer matrix between the plane wave basis and the focus basis, and then it's only a Fourier transform. Or you can use the green function between the transducer basis to the focal plane to propagate the data from these transducers to the point inside the medium. Okay? So like that, you can simply change the basis by just applying matrix product on the right or the left of the reflection matrix. And you can, as I will show you, you can study important quantities such as the time reversal invariance. You can perform singular value decomposition because you are first in the Fourier domain. So let's see what looks like this focus reflection matrix in a phantom. So a phantom is a tissue, it displays the same mechanical properties as a tissue, and especially it shows an ultrasonic speckle that is characteristic of what we have in the human body. So we often use that to first characterize our methods. Okay, so to project the reflection matrix in the focus basis, I start from this matrix, theta in UART, theta in is plane wave basis, UART transducer basis, and then I apply the transfer matrix in the plane wave basis and in the transducer basis on each side of the reflection matrix. This operation consists in focusing in transmit mode, but everything is done in post-processing here. Okay, we don't focus physically inside the medium, but we do it thanks to the reflection, all the information contained in the reflection matrix, and then you can apply the same operation at output. So at the end, you obtain the impulse response between one point R in here and one point R out here. But the size of these virtual transducers are still limited by diffraction theory, meaning that as we are in the Fourier domain here, the focal spot, it displays an elegant elongated shape, okay, like a cigar, with an axial resolution, which is given by the depth of field of your probe and related to the depth Z and the aperture of the probe. Okay, so if we want to, so if you plot this reflection matrix here at a specific depth, what you see is the following shape. We have most of the energy close to the diagonal. Why? Because here I am in a single scattering regime, meaning that when you focus at one point, you only collect energy coming from this focal spot, okay? But the problem here, so here we are at 25 millimeters inside the phantom. As we have a very bad axial resolution, even if I'm focusing at this depth, I can still see the reflectors that are out of focus because my cigar-like shape is is quite thick. And so we need to retrieve the axial resolution of the ultrasound images. And to do that, I will do the following operation. I will sum this monochromatic reflection matrix over frequency. So it's a coherent sum. So you can see it as a Fourier transform at the time t equals 0. And this time t equals 0 is the ballistic time. It's when this virtual source emits the wave. You just collect the wave field coming just after this firing. Okay, and in that case, you see the reflection matrix that was like that, with signals that was spreading a bit out of diagonal because of these out of focus scatterers. Now it's perfectly diagonal, and we are in a single scattering regime, so everything is fine. And if I want to build an image of the medium, I just consider the diagonal. The diagonal is you focus at one point and you collect ultrasonic wave coming from this same point, and this is the confocal image, and this is the typical signal that we measure when we focus at input and output in B mode or in plane wave imaging. Okay, so now let's consider a in vivo case. So here it's a gallbladder. So this is a vésicule biliaire for French people that is close to the liver and that stores biles the liver creates and uses to break down fat. And so this is an important organ because you have often ultrasound diagnosis for this organ because you can detect inflammation of the gallbladder or detect some gallstones. But this image can be quite awful sometimes. In particular, you see here normally it's a pear-like shape. So you should have something like a black disk, very nice black disk, and here it's very blurred by, we will see, by aberrations and multiple scattering, but we will quantify it thanks to the reflection matrix. So we record the reflection matrix on this gallbladder, and then we look at the focus reflection matrix at this depth, for example. Okay, so now, compared to before in the phantom, now you see that you don't have a particular surintensity along the diagonal. Actually, the energy spreads almost, not everywhere, but it's decreasing slowly with when you go off the diagonal. So, as I told you, the diagonal elements corresponds to the one that we use for the ultrasound image, and they are mainly associated with a single scattering contribution. But you have, if you look at this signal along the anti-diagonal, you can quantify the different phenomena that you have in your medium. So you have this single scattering peak that corresponds to the signal along the diagonal. Yeah, I just took the average over all the anti-diagonals of the reflection matrix, incoherent average. And you can show theoretically that if you are in a spectral regime, it gives you an information about the quality of focus at input and output. It's a convolution between the incoherent PSF. So the spatial extent of this guy tells you about the aberrations. And this is here, the width of the diagonal gives you an information on the local point spread function at input and output. And then on top of that, you have a white background, a multiple scattering background, that is due to this kind of path that are associated to the same time of flight as singly scattered echoes, but that are scattered before reaching the focal plane, and that are scattered twice, for example, before coming back towards the array. Okay. Okay, so we have this, all this information. So we have also noise, because noise will appear as something flat. You can also discriminate between multiple scattering and noise with the spatial reciprocity, because your reflection matrix is supposed to be symmetric, and noise is not symmetric. So you can, using this information, you can discriminate between these two contributions. So now, let's find some indicators of the focusing quality. So I have this gallbladder with a very bad image quality. So first, I can quantify the aberrations by introducing a first parameter, which is a focusing criterion. And this focusing criterion is just, so before I showed you this curve, I just look at the width of this single scattering contribution, this width here, and then I compare it to what it should be in an ideal case. And it gives me an important information, because it's a parameter that goes from 0 to 1, 0 bad focusing, 1 perfect focusing. So I can probe this focusing criterion locally. So I can tell you, in that part of the image, it's blue, you're correctly, your image is correct, and you can rely on this part of the image. But here, your yellow, it's awful, you cannot see. And honestly, when you look at the image, it's impossible to know that you are not so well focused here and that you are very well focused here, because it's only you are in the fog. You are in the fog of speckle. Okay, so it's a very important information for diagnosis. And then you can also on the focusing criterion, you see there are white areas, and these white areas are areas where actually multiple scattering is so intense that you cannot see clearly a single scattering contribution, and so you cannot assess the focusing quality. But you can still, by looking at the ratio between the single scattering component and the multiple scattering component, retrieve a multiple scattering rate, okay, between 0 and 1. 1, so here it's not only multiple scattering, there is also noise. But for example, here it means that you have only noise or multiple scattering, so you cannot say anything, and you will not be able to retrieve anything at this location. Of course, it increases with depth, and you see that some parts in tissues are more strongly scattering than the others. Okay, so it's an information maybe you can use to quantify the microarchitecture of the tissues. But first, let's try to compensate for the aberrations inside this image. So, what people usually do in acoustics, in acoustics or even in optics, in adaptive focusing techniques. They send a focused wave at a given point, and they collect the wavefront coming from these points. And if you build an image, apply time delay and so on, you have a very bad signal because your focal spots are very distorted by the aberrations. So what you can do to retrieve an optimized focusing law, this is what explains Matthias yesterday. You can cross-correlate the backscatter decoys, and then you will obtain a focusing law. It may be not very correct, but still you have a focusing law that corresponds to, ideally, the signal that you should apply in emission to focus perfectly inside this pointer in, and the same thing at reception. So why this cross-correlation between backscatter decoys work? So we can show it with a matrix formalism, and I will show you how the matrix formalism allow you to go beyond this simple cross-correlation. So let's take the focus reflection matrix. So what we do, so we have a set of input focusing points inside the medium. And then, now I will come back towards a correction basis. So here I will consider the transducer basis, but you can consider whatever basis for correcting. And for example, in this case, it will be very nice to project the data in this plane, because this is where the aberration is. We'll see after why. Or you can project in the plane wave basis, I mean, whatever basis you want. And you will analyze the reflected wavefront in that basis. So I'm focusing at that point, and I will look at the shape of the reflected wavefront. Okay? So you have this dual reflection matrix, dual because you are in between two planes that are almost conjugate with each other, not conjugate, reciprocal with each other. And then this dual reflection matrix, so it shows this tilted wavefront because they correspond to different input focusing points inside the medium. And then the key tool here, the key idea, is to decompose all this reflected wavefront into two components. So already said by Matthias yesterday, you have a geometrical curvature that is the model. Actually, this is what your model expects if your medium was homogeneous. And on top of that, you have a distorted part that corresponds to all the fluctuations that you have compared to your model. Okay? So mathematically, it can be done by Hadamard product between this reflection matrix and the propagation matrix with a phase conjugate. And at the end, you obtain this distortion matrix, okay? And this distortion matrix corresponds to the following situations. It's the same situation as the dual reflection matrix, except that now all the input focal spots have been shifted at the same position. And all the wavefronts before that used to display a different geometrical curvature, here they are all aligned with each other. And if your aberration is spatially invariant, they will look like the same, okay? Only there is only a coefficient, a random coefficient due to the random reflectivity of the medium, but otherwise they are the same wavefront. And then you have strong correlation on this distortion matrix, and this is what you're gonna exploit to retrieve the aberration phase transmittance. And here, this is where comes the cross correlation of your distortion matrix coefficients. So you build a cross correlation. So this cross correlation is between the input focusing points. It's not a cross correlation over time, but between different the different transducers UART and UPROMAT. Okay, so if you build this covariance matrix, it is analogous to a reflection matrix with a coherent virtual reflector whose size is limited by the initial aberrated focal spot. Okay, with the cross correlation, you can add all these incoherent virtual sources. You can rephase them between each other and then add them constructively. And this is what you obtain. And so, for example, you can simulate what will give a plane wave emission through an aberrating layer. Okay, so this aberrated wave field is scattered by the coherent virtual reflector, and then you can record this scattered wave field. Okay, and this scattered wave field comes from this point. So even if this incident wavefront was a bit aberrated, imagine that this guy is point-like. It will give you directly the aberration phase transmittance. Here it's not the case because your coherent virtual reflector is a bit big, your guide star is a bit blurred, so this wavefront is not perfect. So what you can do is to iterate the process. Phase conjugate it, time reverse it, and then send it back to the correlation matrix, okay? And if you do that, you will compensate most of the aberrations inside the generated by the aberrating layer, and then you will focus not perfectly, but in a much better way compared to before, okay, on the coherent virtual reflector. And you can do it many times, okay? This, you can perform what we call an iterative time reversal process that used to be done physically by Matthias and Claire Prada in the 90s, but now you do it everything in the computer. And at the end, you obtain a time reversal invariant of your correlation matrix, which is nothing than the first eigenvector of the correlation matrix, okay? And the phase of this first eigenvector is the estimator of the aberration transmittance. This is the distortion that allows you to compensate, if you phase conjugate it, that allows you to focus perfectly at the center of this virtual reflector, on the brightest part of this virtual reflector. Okay, so we can do that. We can use this result. And then you can, so I get my estimator of the aberration phase law. I add the geometrical component that is related, that is dictated by the point I target inside my medium. And then I apply these time delays on my array, or on my reflection matrix, I apply this aberration phase law. And then I will focus inside the medium with a nice compensation of all the speed of sound inhomogeneities inside the medium. Okay, and then you can tilt this aberration phase law, okay? So you tilt you assume that the aberrations are spatially invariant in all the medium, and then you can tilt this aberration phase law, just changing the geometrical component, and then you can retrieve an image, a diffraction limited resolution image in that part of the medium. But of course, this has a limit, because the aberration phase law that I found is limited over an area that we call the isoplanetic patch. And this is the area from which the aberrations induced by the medium are spatially invariant. And this isoplanetic patch, it can be quite small, actually. It can be of the order of 1 millimeter in your image, or even smaller, actually, for high-order aberrations. So it was really the limit of adaptive focusing techniques in general, because people usually do all this process in a physical process, but it means that you have to learn about the medium in every isoplanetic patch, learn about the aberration phase transmittance, and then iterate the process, etc. It was not possible for practical applications to do such things, especially when the medium is moving. So, yes, so this, if you apply, when you apply a different, a geometrical component that is too far from the initial point, then you go out from the isoplanetic patch, and then you get you don't compensate properly the aberration, because your incident wave field is not going through the same area of your medium. Okay, and even so you have also this the dimension of the lateral dimension of the isoplanetic patch, but you have also a finite extent of the isoplanetic patch in depth. So you have the same problem in depth. So you have spatially distributed aberrations. So that's a big problem. So what you can do, you can either use the full distortion matrix, do singular value decomposition, and look at the different eigenstates, but it works only for aberrations that are only changing with depth. But if you are in a more complex case where aberrations are changing both in the lateral dimension and along the axial dimension, you should perform a local distortion matrix analysis. So consider spatial windows where you will estimate the distortion matrix, look at its covariance matrix, and retrieve a focusing law for each area inside the medium. Okay? So of course you have a compromise that has to be made between the size of the spatial window, the number of input focusing points you have inside the medium, and this guy, which is the number of resolution cells mapping the aberrated focal spots. So it means that if you have strong aberrations, you need a lot of input focusing points to converge towards the satisfying aberration phase law. So this is a compromise, but then you can you can converge towards a good aberration phase law for any pixel inside the medium by considering an iterative aberration correction process where you gradually decrease this spatial window, and then you can address more complex aberration phase law, high-order aberrations that are associated with smaller isoplanetic length. And with all this process, at the end, you're able to, so here I'll show you the intensity profile, which was the PSF in reflection I showed you initially. So you remember you had this white background on top the single scattering peak, and you're able to the different steps of the aberration correction process, you're able to move this single scattering peak much higher than the incoherent background. So you improve the contrast of your image, as I will show you now. Okay, so you see the different kind of correction that you're doing. And so you can retrieve an aberration phase law for any area inside the medium. So you see that we see here the notion of isoplanetic patch. The aberration phase laws are completely different from one position to another. Okay, so that's why it's very important to compensate locally for these aberration phase laws. And importantly, you need to correct aberrations in the different bases. So in the plane wave basis, it's very important when you have multi-layered medium with different velocity. In the transducer basis, it's very important to compensate for all the aberrations that take place close to the surface, typically the skin, the fat, etc. So you really have to jump between these different bases. And in other case, you can have a strong aberrating layer at a given position, and you will need to compensate in this plane, in a plane close to this aberrating layer. So in terms of imaging, so this was the initial image. So you remember you have the thinken wall of the gallbladder that we could think about inflammation of this gallbladder because you have the thickened wall, and once you compensate for the aberrations, so I just move the movie, so you now have a perfectly shape gallbladder, so it's important for the diagnosis. And if you look at the focusing criterion and the multiple scattering rate, you see that now your image is drastically improved at small depth, and also in some parts at large depth. That was not at all before. Okay, but still, it's not perfect. You still have some part of the image that you cannot compensate for. And probably here you will need not only phase conjugation of your transmission matrix, I told you, but also inversion, because some parts of the first layers are more attenuating than the others, and you will need to compensate for that. But of course, you will have problem also with electronic noise and everything, so this is something that we are working on. And in terms of multiple scattering rate, you see that you now have a much better contrast over a major part of the ultrasound image. So now you can be confident in the image provided by the ultrasound matrix imaging process. Okay, so this was the first proof of concept of the matrix imaging process in ultrasound imaging. So you can compensate for aberrations, for example, for detecting microcalcification in the breast, as explained already by Matthias yesterday. But you can also, we have plenty of things that we are working on, but Elsa is working on the multiple reverberations with this simple academic experiment where you have a plexiglass layer between the probe and the tissue mimicking phantom, and you see that this plexiglass, of course, generates a lot of multiple reflections, in our data. So we are not able to retrieve, for example, the target here because we have all these reflections, and you see that you have ripples behind each target that is due to these multiple reflection events. And by using these matrix imaging tools, we are able also to compensate for the axial aberrations that we have. So all the multiple reflection events, you can compensate for them, and at the end you obtain a much better axial resolution. You are able to remove that part, the first reflection due to the plexiglass, and behind that we are able to retrieve the target with a much better axial resolution and a better contrast for the most ecogenic structure. So can have also applications, as I will show you, in passive matrix imaging, in a passive seismology. This is the second part of my talk, where I will discuss the applications of the method I showed you in the ultrasonic context to seismology. Okay? So, you know that, of course, seismic wave can be used to image the inner structure of the Earth. So you can study it in a transmission configuration at low frequencies. And then you can, we have seen some talks here where you can study the different arrivals of these different waves following different trajectories inside the Earth. But here, I will not consider these configurations that I call transmission configuration, but I will consider reflection configuration that have been used in seismology more at the local scale, okay, where you are using some man-made impulse, seismic impulse, to probe the Earth at over 1 kilometer depth, typically. So you have a vibrating truck, for example, that emits a seismic wave, and then you look at the reflected wave field on an array of geophones, and then you can move this truck and record the reflection matrix as we did in acoustics. So, so this is exactly what I explained. So this is based on this information, you can apply migration techniques that allow you to retrieve to build an estimator of the reflectivity of the underground. Okay, so it's well suited to image horizontal structures, as we see here, but it fails to image the vertical structures. And here we just detect the fault because of the discontinuity between the reflectors on each side. On top of that, migration techniques, they need a very accurate velocity model, and in the area I will investigate today, it's everything but true, and actually it's a big problem for migration technique. And of course, you need a high computational effort to make your migration algorithm work and converge towards a good solution. So you have a lot of computation to be done. And the reflection matrix analysis I showed you in the first part, it's really more flexible, and in terms of computation, it's not so heavy. Okay. So you have the problem in active seismic imaging. You have also a limited penetration depth because you cannot send a very large. You cannot inject a lot of energy inside the Earth. It's problematic, of course, because of environmental factors, and it's also, of course, very expensive to settle all the equipment for this kind of experiment. Okay, so of course the alternative is the passive imaging methods, for which we are all here. So I will not explain to you what are correlations of noise, but we can still record the noise between 2 points and then cross-correlate it, and then you get the information that you would have if you had induced a mini-earthquake at A and record the wave field at B. So you obtain this Green's function, and this Green's function for us, it's an impulse response between A and B. So you can imagine, of course, that if you have an array of geophones, you can get from the cross-correlation of seismic noise all the response between each geophone of the array, and you get what we call the reflection matrix. So usually, I mean, we have seen some work during this workshop where body wave have been used, but generally, most of the passive seismology is dedicated to the study of surface waves, okay, as shown by this nice paper by Nikolai, Michel, Anne, and I don't remember the fourth one. Anyway, so we have a tomographic is here, the one that Laurent. Okay, sorry, Laurent. We have a tomographic image of the Rayleigh wave velocity. Okay, but now what happens for body waves? Can we use the body wave contribution and use the reflection matrix tool to learn how to focus deep inside the Earth, especially in complex heterogeneous areas. Why it's important? Because in reflection, you have many contributions to your to the bulk wave reflection. So you can, of course, detect the interface between geological layers. Okay, so we have what we call specular reflections. You can also detect some more short-scale inhomogeneities, and in that case, I will talk about scattering. And you can also have what we call diffraction. So this is, for example, what arises at the corner between two geological layers like that, typically along a fault area. And this scattering and diffraction, generally, they are not really used, resolved by migration techniques. And actually, here, this is what we're going to use to learn how to focus inside the medium. And this is what we're going to image as well. And we'll see that there is a lot of information inside these contributions. Okay, so here I will apply it to fault structure and volcano structure. And these two areas are very complex. Okay, you have the fault core, where the wave velocity, you have, the damage zone that surrounds the fault core, that is very complex areas with a smaller wave velocity, a lot of cracks and fractures. So this is very complex to image because you have, as I will show you, you have strong aberrations. And you have also the volcano structure that is made of a complex plumbing system with dikes, chimneys, reservoirs of magma, and we want to image all these things along a penetration depth of the order of 20 kilometers here. For the fault structure, I will show you today local scale application, but there is a poster of Rita that you can go and see with Michel that did an image of a large scale area in the North Anatolian, along the North Anatolian fault. So, what kind of problems that we have in reflection seismic imaging? Exactly the same as in ultrasound imaging or optical microscopy. These reflection imaging methods are based, most of them, on the single scattering assumption. But, of course, so in that case, if this is true, you can still use the travel time to get the scatterer position. But, of course, here you have strong variations of the wave velocity that induce, of course, aberrations, and you can have also refraction, etc. So it can be, it can induce a great loss of resolution and contrast on your image. You can have multiple reflections, as the experiment I showed you in ultrasound experiments, and you can have also, as in ultrasound imaging, multiple scattering. So meaning that you have a strong concentration of scatterers, and the wave is scattered several times before coming back towards the array. So we have exactly the same problem, and so the idea is to use the tools that we developed in acoustics and to transfer it to passive seismology. Okay. So first case, the San Jacinto fault zone that we've done with these people, so Rita and Michel, Thibault and Arnaud de Rode. So this is an array of geophones that had been settled by, I think, Benzion. No, yes, I don't know. Yes, yes. Along along the San Jacinto fault. So it's a huge number of geophones. So it's very, the distance between the geophones is of the order of 10 or 30 meters. So here we will consider a frequency bandwidth where the wavelength is much higher than this interstation distance. So we check the Nyquist criterion. And this is actually the condition that you have to check for the reflection matrix, if you want to use it for imaging, is that you need to have an interstation distance of lambda over 2, approximately. Well, it can work with lambda, but still it's the order of magnitude. Okay, so Philippe Roux, in this paper, and co-authors already studied this cross-correlation of seismic noise induced by ocean wind and humans in the area, and they managed to extract the Green's function. Here, this is a different impulse response that is plotted as a function of distance between the stations. And you see the first arrivals, and you can see the relay waves that arrive in the trace of the data. okay? So we can have access to all this impulse response between any geophone, and then you can analyze it under a matrix formalism. So if you consider the reflection matrix in the geophone basis, so you have the emission reception as a function of time, so you can take a specific time, and if you look at one column of this reflection matrix, it corresponds to the wave field that you obtained for a virtual source at this given position, okay? And so if you look just at the data, so you can well see the contribution of relay wave, but on top of that, you have some contributions coming earlier, and that are probably due to body waves scattered in depth and coming back before relay wave reach this point S out. Okay. But this basis is not very convenient for imaging, and as we have done before, you can focus inside the medium and look at the impulse response between virtual geophones inside the Earth, okay? So we do exactly as in acoustics. We consider this reflection matrix in the frequency domain. We apply free space, so here Green's function if you want. We consider a very simple model, very rough, just constant wave velocity. And so we apply this free space transmission matrix. It generates cigar-like shape geophones, and then I can retrieve the axial resolution provided by the large bandwidth of the seismic signals by summing the reflection matrix, the focus reflection matrix in the frequency domain over the frequency, and you retrieve an axial resolution that is now just limited by the frequency bandwidth. Okay, exactly as in acoustics. So this kind of manipulations were already done actually in geophysics. So this is the work, for example, of Wapner. They call it redatuming in seismology. But on top of that, now we can study the focus reflection matrix and look at the different information that you have in this reflection matrix. So here it's R in, the position of the input focusing point, R out at output, the position of the virtual receiver. So remember that if we had no aberrations, multiple scattering, if everything was perfect, all the energy would be along this diagonal. This is far to be the case here, and actually it's more, even worse than, much worse actually, than in ultrasound imaging. So if you want to build an image of the medium, you can look at the diagonal. You have a confocal image. This confocal image corresponds to this situation. You focus seismic wave at one position and collect seismic wave coming from the same point. But you know that you cannot be confident in this image because you have a lot of energy outside the diagonal, and this energy is due to the bad focusing process that you have in depth, okay? So if you look at one anti-diagonal of this reflection matrix, it gives you the local PSF, okay? It's actually the convolution between the input PSF and the output PSF. So if you had no aberrations, all the energy will be contained in this white circle, which is the diffraction limited resolution. Here you see they have plenty of energy everywhere, so you have some energy around it, so it means that you still have a memory effect of your ballistic wave, approximately, but on top of that you have aberrations and maybe some multiple scattering. So how to compensate for these complex phase distortions that we see in the reflection matrix? So I forgot to say that you can, of course, do this process at any depth, okay? And you can retrieve a three-dimensional image of the fault, but this image is very blurred. It's like you're in the fog. You don't see anything because you have too much aberrations. Okay, so here it's one example, a cross-section view on this part of the San-Jacinto fault. So to compensate for the aberrations, I do exactly the same thing as I did before for ultrasound, except that here I will not study the dual reflection matrix in a geophone basis, but I will project the data in the Fourier basis, in the plane wave basis, because you have often multi-layered wave velocity distribution in this kind of area, even if it's not completely true, of course, because you have also lateral variation, but still it's, as I will show you after, it's a very nice basis for seismic applications. So you have your matrix in the focus basis, you project one side in the plane wave basis, you remove the tilt due to the geometrical focusing at different points, okay? So this is what is predicted by your model of propagation. And then you have this wavefront that superpose to each other because these 3 points were in the same isoplanetic area, okay? And after, you do iterative time reversal. Mathematically, it's equivalent to SVD. And you obtain, if you're lucky, a first eigenvector that gives you the aberration phase transmittance, either at input or output, of the inhomogeneities that describes the inhomogeneities of wave velocity, of bulk wave velocity inside the medium. So it yields, okay, so we can do that. So I forgot to say that here we record the vertical polarization of the wave field at the origin. I forgot to say. So apparently it's more P wave that we should detect in that case when we focus at depth. So we are in a sparse scattering regime, and mainly it will be justified a posteriori, but we have a few scatterers at each depth. And in that case, it's quite convenient because you have directly a one-to-one association between the eigenstates of the distortion matrix and the isoplanetic patches. So it means that you can use several eigenvectors to focus on different locations, different isoplanetic patch in the medium. So this is what we do here. We retrieve aberration phase law, just looking at the first singular vectors in the plane wave basis of D. This is the phase of these singular vectors. We use them as focusing laws, new focusing laws, to project the data in the focus basis. And this is the kind of result that you obtain. So this was the initial point spread function, aberrated focal spot. And then after application of this focusing law, you see that this focal spot is now very thin, centered around the targeted position, in both isoplanetic patch. And you see the image that was originally very blurred and very low resolution. Now you see different parts of the Kark fault. Okay, here in the northwest, here just on top of the fault. So here it's just at one depth. And what a very important property here, very surprising, is that the resolution is actually much better than what you expect, what you should expect in free space. So we'll see why after. Okay, so this is the kind of image that you can build by doing the same process at any depth. And this is the image that you obtain. Okay, so originally the image was very blurred. Okay, you can't see anything. Now, what you can see is a strong damage area here at the surface. And this damage area goes until 1,000 or 500 meters. And then you see the position of the fault just by looking at the interface between geological layers that are different. The network of Geophone layers is different on each side of the fault. So this is something that you can reveal with the matrix imaging process. So this is a kind of you can detect a lot of informations. I will show you after, but I just want to try to interpret this lateral resolution. So here we are in a situation where you have a fault, and so a priori the wave velocity is smaller in this area than you have a lateral increase of the wave velocity on the side of the fault. So normally, as I said to you, if you considered the ballistic wave, suppose that you propagate in a homogeneous medium, you will have only this path that can reach the scatterer. And so the resolution is given by lambda over 2 sin theta, where theta is the angle under which you see the array of geophones. And actually, we found a resolution which is much better than that. So one possibility, and we'll see in the volcano, we'll have the same result, and I will try to show you more, we'll try to dig a bit into that. But one possibility is that you have some kind of channeling of waves between the geophone basis and the scatterer. And when you project your data in ski space, actually, these waves, if you are in the geophone basis, all the information is over the geophone array. You cannot get information here, okay? It's limited by your data collection. But in the key space, you can collect these large angles. And actually, the support of the singular vector I did not show you here is much wider than what you expect if you were in a ballistic configuration. So in acoustics, we have never things like that. In acoustics, we are still limited by, we don't have any channeling or whatever. But in seismology, actually, you detect waves that are coming from a very high angle. So you can also have maybe relay waves that contribute, relay waves that propagate through the surface and then are focused back. This is what Matthias said yesterday. But anyway, at the end, you seem to have a coherent image with a very high resolution, so it's a good surprise. Okay, so then Rita and Michel made a huge work to interpret all these images. So I'm not an expert, so I will not explain to you, but this is the kind of image. So movie is not working, I don't know why, sorry. It's always like that. Okay, well. Sorry, so it should have worked, but anyway, so you see in the different parts, so we scan the fault zone either in this direction or in this direction, and on some part of the image, you see clearly the geological layers. It's where you have a small damage area, so you can see easily these geological layers, but on other parts, you have a more complex structure. So this is what we look at now. So you can look at the fault zone at the few hundred of meters depth. This is what Rita did. You can compare along the north direction or along the west direction, and you can see very different behavior. On one direction, you're along the fault. You don't expect variations of the structure, of the internal structure of the fault. So this is what we see. And when you're crossing the fault in this direction, you see very different behavior, very different mechanical properties of the fault between each branch of the fault. Okay, and this is in coherent with previous shear wave velocity tomography performed at Grenoble, I think, in this area. Except that we seem to have, of course, a much better resolution because we are looking at the reflectivity and not only at the shear wave velocity. Okay, so here, for example, if you look now in depth, what happens? So when you are in this part, in the north of the area, you are able to see geological layers, and you have not very intense damage in this part. Whereas in the south, it's much more scattered. You see signals everywhere, so it seems that there is an ongoing generation of rock damage in this part. But again, I'm not an expert, and I'll let Rita and Michel discuss maybe after the presentation to discuss about the interpretation of these images. So now I switch to the La Soufrière volcano that has been investigated by Elsa, who is there, and Arnaud Burtin from the Institut Physique du Globe de Paris. And it's now, so the network of Geophone is here much less important than what we had in San Jacinto. 65 geophones, and you see that the array is a bit scattered. So there was a question yesterday, and actually it's not a big issue in our case, as you will see, because we can use the heterogeneity of the medium somewhere to get to regularize our imaging problem and get a very nice resolution, nice focusing process inside the medium. So the interstation distance here is of 200 meters. We are working still in this frequency bandwidth. So you see here we are not really checking rigorously the Nyquist criterion, but it still works. This is the power spectral density of the seismic noise. So you have different sources of seismic noise, but we have most of in the frequency bandwidth that we are looking at, it's most due to fumaroles that are taking place in the volcano. Okay, so you can record you can perform the cross correlation, and you obtain cross correlation data that allow you to estimate the wave velocity, the shear wave velocity, and the P wave velocity at the surface, and they are very low because we are in a volcano, very complex area. Okay, so so we do exactly the same process, just to show you that the process is flexible. You can consider more complex seismic velocity model, okay? It's always, of course, it's always better to use the better wave velocity model you can have. So here, ELSA used a multi-layered model to first project the reflection matrix from the network of geophones inside the volcano. We get this reflection matrix. We can look at the PSF, the point spread function, so it gives you the focusing quality, as I told you before. And as in San Jacinto, you see that the focusing process is very complicated in this area, and you have a lot of energy outside the position that you expect. Okay, so this is due to aberrations, and this explains why the original confocal image is, of course, very blurred, and something you are in the fog as before. And actually, the results look like a lot San Jacinto initial results. Okay, high aberration level, and then you can perform all the story I told you and estimate the aberration phase law. So you see this kind of aberration phase law, quite complex, to focus through the heterogeneities of the volcano. And here I'll show you the modulus of U1. You will see after why it's important. It gives you the support of angles that you collect with your array of geophones, okay? When you try to focus at one point in depth. So if you do this correction, phase conjugate this aberration phase law and apply it on the data, this is the kind of PSF that you obtain, okay? And again, we have this super focusing performance. So not that this super focusing performance, we don't have it all the time, okay? For example, in the large scale area that Rita studied in the North Anatolian fault, along the North Anatolian fault, we don't have this kind of area. So it's really related to the heterogeneity here at the local scale of volcanoes and fault areas. Okay, so we obtain this kind of image. You can imagine a chimney with some complex plumbing system. We'll see in 3D, then it will be a bit easier to analyze. And here we have a resolution which is at least 4 times better than the diffraction limit. And again, we can have the same effect as in fault zones. So here, this is, ELSA showed actually what is the support of the eigenvector of D when you analyze the aberrations in the geophone basis or in the key space. And you can translate them then into angles if you want to compare them. And actually, in the geophone basis, as I told you, the support of this eigenvector is very small. It's limited by the array. And you see the shape of the array with a few stations that are outside the core of the network, okay? And when you analyze the data now in the key space, it's much spread, okay? You have a much larger support, and you seem to see different trajectories inside the medium that you manage to recombine to focus at a specific location inside the volcano. So it's a I think it's a of course, it's not still, we have not investigated, I have not tomography of this volcano, so I cannot be 100% sure, but this is something that has already been investigated in transmission, in waveguide by Philippe Roux and Matthias, when they look at time reversal experiments through a waveguide, and they add exactly the same kind of focusing properties. So when you look at the final image, 3D image of La Soufrière, so you can, so we have this conceptual model of La Soufrière from this paper. So you can find maybe some analogy between them. That maybe there is still a work of interpretation to do on this image, and we will need the help of geophysicists, of course. The crystal mesh, which is made of a complex network of magma reservoir, with maybe something that we can see here, and we have the chimney at the surface that goes towards the surface, and we can look, correlate with the seismicity in the area. So it's like we have an endoscopic image of La Soufrière because we are using a waveguide channeling. You know, generally endoscopy is like when you have for example, fiber, optical fiber, or something that you put inside the body to look, to be able to image inside the body. Here, we use a natural wave velocity distribution inside the medium to build a high-resolution image of its reflectivity. Okay, and you have also the superficial conduit that we have strong correlation with the location of seismic noise that has been computed by Arnaud Burtin. So the movie, I don't know if they seem to work approximately. So this is the kind of image that you obtain. So you seem to detect still when you're far from the bottom of the volcano some geological layers as before, but just beneath the volcano you have a very complex structure that you can see here with seismicity. So of course, I don't know if you can directly correlate actually the seismicity with the image, because seismicity is based on migration techniques that are not considering the wave velocity distribution. So of course they are also affected by aberrations. So that's why you can have a different behavior between different behavior. For example, this part is not exactly aligned with our image, but maybe our image will help in the location of these seismic events. Okay, so just to conclude, I have a few things. I don't know what time is it. I still have time. Okay, so I have things to show after. I just wanted to conclude on these matrix imaging parts, where we have been able to reach quite large penetration depth at high resolution. And of course, there are a lot of things to do still, because here we don't correct for axial and dispersive aberrations, and you have a lot of these issues. Actually, the image I show you each time, I told you it was as a function of depth, but it's not as a function of depth. It's as a function of the time of flight. Okay, so we have this kind of repositioning of try to find the good depth for each scatter we detect, and I will show you how we can do it just after. And of course, you have all this story about P wave, S wave. Here we are mixing everything, and we use a very rough wave velocity model. But of course, there are conversions. There are probably P wave, S waves. We are correcting all them together. So maybe there can be some tools to address them independently and address their conversion. But there are many things to do to improve again the image. It's a preliminary step of a more complex story. Okay, so these are the perspective. We can compensate also for multiple reverberation, address the multiple scattering issue. Here, I just correct for wave velocity inhomogeneities, but of course, you can, for example, in this volcano, the very robust volcano that we studied with Michel and Arnaud Dorode and Thibaut Blondel and Julien Chaput a few years ago, we did not use all this trick, just a multiple scattering filter, and this volcano is very multiply scattering. You have a scattering mean-free path, which is the order of the wavelength. So it's very extremely scattering. So we managed to detect the big structure inside it, but we did not use multiple scattering to improve the focusing process. So this is something that we plan to do in the next few months with Rita. So how to go towards quantitative matrix imaging? Because here I only showed reflectivity images, so fluctuation of the impedance approximately, but not very. It's useful, but you're used to build maps of wave velocities. You like that, and we love that also in acoustics because it can be very useful for diagnosis, as I will show you after. So if you want to access to more information inside the medium, here we have played only until now at one depth and looking at the response between 2 points at the same depth. But nothing forbids to look at points located at different depths and at different times. Okay? So let's do that. So, and this is done just by now looking at the time lapse between the input and output focusing points. So I come back to acoustics, okay, to test our ideas, much easier. Focus at one point and look at the wave field just close to it, in depth and in lateral, in the lateral axis. Okay, so what we get, this is something like that. Just show you. So what we see actually, we use all the scatterers as microphones, and these microphones help us to follow the wave field inside the medium. Okay, so generally, we just look, just before I just showed you what we collect here, and just at time t equals 0. But you see that you can look at the wave field outside this focal plane, and you can make a self-portrait of the ultrasonic wave focusing inside the medium. And here, everything is good. The wave velocity model that we use matches with the true wave velocity inside the phantom, so the focus is perfect, and everything is nice. So now what happens if, for example, what happens if I use a wrong wave velocity model, okay? A larger wave velocity model, wave velocity than the reality. But now you see that your wave field is focusing just above your targeting, the targeted plane, okay? And you can use this information to try to estimate the wave velocity inside the medium, okay? The same at if you make another error. For example, if you are underestimating the wave velocity, you will focus behind the targeted focusing point, okay? So the idea now is to do that for any point in the medium, any point are in, just looking at the focusing process like that in the spatio-temporal domain, and measure a wave velocity, an effective wave velocity for each point. And this is something that has been done by Flavien Bureau during his PhD thesis. So here he looked at the ultrasound image of a difficult-to-image patient, means obese. Okay, so you have a large, you cannot see it on the ultrasound image, but you have a thick layer that I will be able to extract thanks to wave velocity. It's very important to measure the wave velocity in liver because you can detect some particular disease, steatosis, which is an accumulation of fat droplets inside the liver. And when you are sick, you have a wave velocity in the liver, which is very weak, which is weaker than what is expected. Normally, it's this value that you'd expect, and it can go until more 1,500 meters per second if you are very sick. Okay, so it's very important to measure the wave speed here. But the problem is that you have different layers to cross. You have the skin, you have the fat, muscles, etc. So what we do here, so Flavien, what he did exactly the same movies as before in speckle. He combined all the speckle grains together, do the SVD, things like that, to simulate a coherent reflector at any point. And then he gets a movie. And then from the focusing that he gets, from the time lapse in the focusing process, he can get integrated speed of sound for any point, okay? So this is the integrated speed of sound, integrated from the probe surface to any point inside the medium, okay? So this is not the local wave velocity. And of course, you need to inverse the problem, to retrieve the local speed of sound based on this map, and this is what is done. So the algorithm is very crude here. I think you have much better tools than we do, but anyway, we can, with this example, we can find the layer of fat with a very low wave velocity, so huge layer of fat, muscle fibers just behind, and a fatty liver, because the wave speed was estimated to be of the order of 1,480 meters per second. So the patient has officially a steatosis. Okay, so it's just an example to show you that the matrix imaging can be a useful tool for a tomography of the speed of sound, and of course this kind of thing can be done also, we hope. I will show you a few preliminary results of Rita and Michel that we obtained in the North Anatolian fault on this topic. And just to tell you, you can use this information also to now obtain an ultrasound image, not as a function of time or an effective depth, but of a true depth, because now you have the true velocity inside the medium. So you have the true, even with the integrated velocity is sufficient actually, you can correct now the image in the axial dimension and retrieve the exact position of all the scatterers that you detect on your image. And it can be very important because a large part of the diagnosis in ultrasound is to image distance. And for example, for the, I don't remember the name in the clarté nucale, for the diagnosis of some disease, it's very important because below 1 millimeter it's okay, larger than 1 millimeter is not okay. So it's a very important tool. Okay, so and we can do that also in seismology. And in seismology, I guess you're very interested in knowing exactly the depth of your layers and not only the time of flight. Okay, so this is the preliminary result from Rita during her PhD thesis. And this is the kind of wave field focusing she obtained at a given position. So it was, sorry, a North Anatolian fault. And she focused on that point and look around what happens. So I redo the movie. So you see it's very similar as in acoustics, except that I am not in a phantom, okay? It's a real medium, so it's not as nice, but still there is important information on the focusing process inside that, it's kilometer and not meter. I think it was on the Moho here. So, yes, so you can play this propagation movie with different velocity models. So here we consider a velocity model that is right, at least in terms of integrated wave velocity. So you see that the wavefront is converging and reach the targeted point at the exact time delta t equals 0. So you can say that this model is right. And if you use a wrong model, of course, you will the curvature of your wavefront will not be exactly at the targeted point at delta t equals 0. So you can deduce from this shift the integrated wave velocity, and then you can try to find, once you have this map of integrated wave velocity, you can try to find the local velocity map. But of course, you need to have scatterers everywhere, which is not always the case in seismology, and this is one of the limits. And that's why maybe the Erebus volcano that I showed you that is very strongly scattering can be useful for this kind of approach, can be a good area to test this kind of ideas in the future. So I come to the end of my talk. So I didn't show you, but we did we do a lot of things also in optics, because it's very complicated to image the human body with light, because light is scattered. I mean, you cannot image beyond 100 micrometers normally. And now we are trying we apply this reflection matrix formalism, build a matrix microscope that allows you to go beyond the millimeter depth. And this is quite important in optics too. There are a lot of applications, whether it be for biomedical diagnosis or even for biology studies. With that, I would like to thank you for your attention.